I think I've familiarized myself enough with the AT-Tiny402 to try and do something useful with it. So I thought a temperature sensing PC fan speed controller would be a fun little project. A variable speed PC fan has 4 wires. Pin 1 is ground, and pin 2, 12 volts. Pin 3 is the tachometer signal, an open drain output from the fan, and pin 4 is the PWM signal to the fan to control the speed. So I'm going to need 3 things from the microcontroller. I need to keep time, temperature is a slow-moving target, and the RTC module will do a good job at that. I will need the temperature reading, and the only option for that is the ADC module. And I will need a 25 kHz PWM output signal. There are 2 modules that can do that, the TCA and the TCB timers. Of course, there is bit banging it as well, but there is absolutely no reason to even consider that. The TCA timer has more advanced PWM functions, but I don't need advanced PWM features, just the very basics. Additionally, the TCA timer will not run in standby sleep mode. So I'm going to use the TCB module. I haven't used it before, and I'm sure there will be some quirks to it that will be, let's say, interesting to learn about. Now to configure my test board. I want to install the 4-pin PC fan header into pins 6 to 9. So this is how I have the board set up. 12 volts will be supplied to VBus and connected to the fan through a 0 ohm jumper at R62. The tachometer signal will connect to PA2 here through 0 ohm R61. The microcontroller isn't going to make use of this signal. It's only connected to PA2 so I can have a 4.7 k ohm pull-up resistor. The tachometer signal will only be used to watch the fan speed by the scope. Here I got lucky. The TCB module output pin is PA6 on the 8-pin devices, so I can connect fan pin 4 to the PA6 line through 0 ohm R58. I really was expecting to have to run a jumper wire here, since the pin options are so limited for the TCB module. For power, I'm using a 5-volt regulator here. 3.3 volts should work just as well, but I already had the 5-volt regulator installed, so I'm going with it. I'll start a new MPLabX project. The default microchip embedded application project is the one I want. I'll select the AT-Tiny402 as the device and the PicKit5 as the tool. For the compiler, the latest version I have of XC8 is 2.46, so I'll select that. I'll give the project a name and hit the Finish button. And since I left the Open MCC on Finish box checked, it will start up the MCC first thing. One thing I have noticed with MPLabX 6.2 is that the MCC takes a lot more time to start. Now I think the MCC is more stable now, but it has to take at least twice as long to start up. MCC Classic is still an option, but I have to believe that it will be done away with pretty soon, so I'll just go with the MCC Melody. Again, this part seems to take a bit longer than it used to. I do like that there is some visual indication of what's going on. And here we are. First thing I'm going to do is set the pins up. I do have an LED connected to PA1. I can use it for debugging if I need to, so that needs to be an output. PA6 also needs to be set as an output. The TCB output will override the output of the port control, but not the direction, if I understood things correctly. I'll give the pins names, but the LED is the only one I would expect to use. I want to start PA1 high, but it doesn't let me check the box. Not sure why. I'll do it manually in the code. I'll turn off the input buffers for the pins I'm not using. That way I don't have to worry about the unused floating pins. I'll now add and set up the RTC module. It starts enabled, which is what I want. I'll select the 1 kHz internal oscillator. Then enable the periodic interrupt timer. The only interrupt I'm interested in is the periodic timer interrupt, so I turn off the overflow interrupt and turn on the periodic interrupt. Air temperature is a slow process, so I think I'm going to go for 2 updates a second for this. Next is the TCB timer module. I'll add that. It's enabled, again, which is what I want. Going to leave the clock input as the peripheral clock undivided. I'll reduce the main clock later. The timer mode needs to be the PWM8. Well, it's the only PWM mode. I need a 25 kHz PWM signal, so I'll set the timeout period to 40 microseconds. 50% duty cycle at start is fine. I do want this to run in standby. The less current the microcontroller pulls, the less heat it will self-generate. I need to turn on the output pin, and I'll just leave the output set to low. Now to the system clock settings. This is a trade-off between power consumption and PWM resolution, and I really don't need much resolution for the fan speed. I mean, fans are sold every day with just 3 speeds. I'm going to go for a bit better than that. At 4x, that gives me a clock of 5 MHz. 5 MHz divided by 25 kHz gives me a value of 200. That is way more than I need. 8x will give me a PWM resolution of 100, and that really is still overkill. So if I go with 16x, that will give me a system clock of 1.25 MHz and a PWM resolution of 50. I'll go with that. Could drop it down one more and still have plenty of fan control. The PWM time period is in the low 8 bits of the CCMP register, and the duty cycle is in the high 8 bits. 32 hex is 50 decimal. The way I read the data sheet, I would think a value of 50 would give me 51 clock cycles. I'm pretty sure this would be set to 49 for timer TCA, so that is a difference there. There isn't much of a section in the data sheet on the timer TCB PWM mode, but I guess I need to read it over a bit closer. Now I'll add the sleep controller. I'll enable it and set it to standby mode. Then I'll add the ADC module. The ADC voltage reference needs to be set to 1.1 volts for the internal temperature sensor. The reference doesn't need to be enabled. It will turn on when the ADC needs it. There doesn't seem to be much power consumption difference for the ADC versus its speed, so it would seem running it faster will mean it is enabled for a shorter period of time. So I'll leave the clock at the fastest divide by 2 setting. Going to leave it at 1 sample. The noise in the 1 sample might actually be useful in adjusting the PWM value. The datasheet calls for a minimum of 32 microseconds of sample time and initial delay. I'll set the sample length to 22. I think that will give an actual sample time of 24 ADC clocks, so a bit over 38 microseconds at this clock rate. Now I will disable the ADC. It will be turned on just for the time needed to read the temperature sensor. I'll enable the run in standby mode. I'll set the initial delay at 32, so that will put me over the 32 microsecond time listed in the temperature sensor section of the datasheet. Input selection will be set to the temperature sensor. And I want to enable the result ready interrupt. All the work will be done from this interrupt. I'll generate the code. I'm going to start in the MCC generated pins.c file. For some reason, it wouldn't let me set the PA1 pin to high, so I will do that manually. Don't want my debug LED to be lit. I may get lucky and not even have to touch it. Now to the rtc.c file. I forget every time. The MCC doesn't have a button to turn on the run in standby mode for the RTC, so I will enable that manually. And update the comment just to give me a reminder. I want the PIT interrupt vector from this file. I will move it to the main.c file. I think it makes things a bit easier to follow this way. Clean out the stuff I don't need in it. This interrupt should get called about every 500 milliseconds. And this is where the ADC will get turned on and the conversion started. With all the delays, once it's started, I think the ADC will run for a bit over 100 microseconds. After this interrupt routine returns, the microcontroller will go back to standby sleep mode and wait for the ADC interrupt to wake it. Now to the MCC generated ADC0.c file. I always like to double check and make sure the run in standby and enable bits are set correctly. I want to move the ADC result ready interrupt vector to the main.c file. Again, clear out what I don't need. A 16-bit variable to hold the ADC results, and then disable the ADC. And for some reason, it doesn't see the ADC_result_T type. Strange. Let me take a look at the ADC0.h file. Yes, it's there. I haven't had to include MCC generated .h files for a long time, and I'm just now getting out of the habit of doing so. Let me compile it. No rule to make target. Something didn't get set right. But after opening the ADC0.h file, it now sees the ADC_result_T type. Okay, I guess it just needed to adjust itself. So now this is what I would expect. Not really sure what was going on there. Now the code to get a usable temperature variable to work with. Temp C should be very close to the temperature in centigrade, so that just makes it easy to work with. I need a persistent variable to hold the PWM value, so I've got a static variable, PWM, and I'll set it to 17 hex, a little below the 50% value. Now the code to adjust the PWM value, I'm going to give it a 1 degree centigrade stable region, and it's hot in the room, especially on the workbench with all the lights and equipment. So if the temperature reads less than 34, it should reduce the duty cycle, and if the temperature is more than 34, it should increase the duty cycle. That's about as simple as it can get. Now to the TCB0.c file. I looked over the datasheet again. I still think that should be 49 and not 50, but I'm fixing to find out. Double check the run in standby and enable bits. Everything looks good here. So here's the function to set the duty cycle value. It turns off the timer, and after update turns it back on. That is going to cause glitches in the PWM signal, I'm sure. Really won't matter for the PWM signal to the fan, but it might for other things. I'll copy this function to where I want to update the duty cycle. Do a compile to make sure everything is okay so far. 2 more items have to be added. I need to turn on global interrupts. I need to start letting the MCC do that, but old habits. And then the sleep command needs to go in the main program loop, but I will disable that for the initial test, 1 step at a time. And now I need to get the board rigged up for testing. I have a thermocouple attached to the top of the microcontroller with some thermal tape. I'm using a bit of PVC sheet to isolate it from the small metal clamp, but I do expect the thermocouple to read a bit lower than the microcontroller. The 12-volt input goes here, and the programming header here. And then the fan. It's a CPU fan, but I don't remember the name of the heatsink it came off of. It's whatever came with the original Ryzen 1600 CPUs. It's got a bit of use on it. The channel 1 scope probe will connect to the PWM signal that goes to the fan. and the channel 2 probe will connect to the tachometer signal. I'm going to set it on a piece of aluminum. The back of it has 3 7-watt 2-ohm resistors. I plan on using it as a tiny space heater, though it is a pretty big chunk of aluminum, but I thought it's worth a shot. And I'll cover it with this piece of plastic. Try and have the air pull across the PC board. It's not much, but I'll see how it works. Now to program the chip and see what it does. Here is the PWM signal to the fan. It floats to about 3 volts during programming, and then it looks like I get a PWM signal for, I'm guessing, about half a second. So I've got a problem. I did end up using my debug LED to make sure I was passing through all the code, and program flow seemed to be what I would expect. It turned out what was killing my PWM signal was the low duty cycle function. And again, I should always look over the errata sheet before using any module for the first time. I just can't seem to learn that lesson. Of course, that is one of the reasons I like looking over the code generated by the MCC. It should have the errors accounted for. And maybe I'm missing something here, or maybe some code didn't get installed like it should have. In looking over the tcb0.h file, there is this tcb0_load_duty_cycle function prototype. But there is also a tcb0_PWM_load duty cycle function prototype, but that function doesn't seem to exist. Whatever the case, the problem here is the CCMPL or CCMPH can't be accessed as a byte-sized register. The entire CCMP 16-bit register has to be accessed, and that involves the temp register. If load top would have been called right before load duty cycle, I think it would have worked, but I still don't like turning off the timer and then turning it back on. So I'm going to set the CCMPL register with the PWM period value, which really loads the temp register, and then load the CCMPH register with the duty cycle value. At the same time, the CCMPH value is moved into the upper 8 bits of the CCMP register. The value in the temp register is moved into the lower 8 bits. So now the CCMP register will have the proper value. So now when I program it, it looks like it should. And I guess it is reading a temperature greater than 34 degrees. Let me up it a degree and see. And program it. Must be setting right on the edge of 34-35 degrees. A reading of 34 will now cause the duty cycle to drop. The channel 2 frequency counter is the tachometer signal from the fan. I would expect there to be 2 cycles per revolution, so 34 Hz would be a bit over 1000 RPMs. Let me check the PWM frequency. .41 microsecond period time, so a bit lower than 25 kHz. Still well within the PWM frequency range required by the fan. Let me see what setting the period to 49 will do to the PWM frequency. I'll change it in the tcb0.c file and where I update the PWM value. Let me measure the time period now with the register set to 49. Since I'm almost positive 0 is one of the time counts, a value of 49 should give me 50 clocks till it wraps around. And yep, right on 40 microseconds. 25 kHz are very close to it. Now that probably is a bug in the MCC math for the time period, because I don't think the oscillator is that far off in this thing. One more thing to turn on and see if everything is working as it should. I will enable the sleep command and see if it all still works. Yes, everything seems good. And can tell the reading is mostly 35, but with some 34s in there. Let me move the threshold temperature up a degree and see how it goes. Yes, it moves down to the minimum duty cycle. I've set the lower limit at 20%. Depending on the fan, some will run at their lower limit if the duty cycle gets close to zero or zero. Others will stop. This one just runs at its lowest speed. Let me change it back to 34 degrees. I did have the resistor heater on for a bit of testing, and the aluminum block sure does hold its heat. It's cooling down a little bit. Not near as many 35 readings as there was a few minutes ago. The air temperature in the room is just too warm to really cool it down. Let me see if I can help that along a little bit. Of course, nothing here is fast, and it may be more of what temperature the aluminum block is at, seeing that the PC board is setting on it. That is dropping the air temperature a bit. That does seem to be working. That is what I was looking for. I'll call that a success. It would need a bit more refinement to be put into use, but it's workable. My test setup needs a lot more thought put into it. The PC board setting on the aluminum block, turns out that was not a good idea. Really just made the resistor heater useless, so that was a fail. But I did learn a bit more about the tinyAVR series of chips, and that's what this is all about. Thank you for watching.